August 1955 Skidar University under the direction of the doctors Marwa KHEMIS. And today I'm going to give a short presentation about positive periodic solutions to the delaysurvival model of red blood cells by schauder'sfixed theorem. And I'm going mainly to focus on four main sections. First, I will begin with a short introduction where I will present our problem. The second section will be entirely devoted to presenting some preliminaries that we need in the sequel. The third section, in fact, is the core of my presentation, where I will show you our main results. And finally, I will mainly start with the graph conclusion. So let me start by presenting our model. So the main objective of this work is to establish some suitable conditions that ensure the existence, unanimous, and continuous dependence on parameters of positive periodic solution for the following first-order nonlinear delay differential equation with an iterative term and nonlinear harvesting one given by expression 1, where A, B, and H are T-periodic functions with respect to the time variable. This term denotes the composition of x of t with itself. H is the harvesting function and tau is the harvest delay. Equation 1, which can describe process of making red blood cells in blood circulation of an animal, involves two types of delays. The first one that depends on both the time and the number of red blood cells, and the other is a constant harvesting lag. More precisely, equation 1 can be considered as a particular case of the following first-order nonlinear delay differential equation, where x of t is the number of mature red blood cells in blood circulation at time t, A of t is the loss rate of red blood cells from the circulation, B of t is the production rate. This term stands for the flux of red blood cells in blood circulation, where tau1, which depends on both the time and the density of mature cells, describes the time delay between the production of immature cells in the bone marrow and their maturation for release in plant streams. This results from the fact that some growth factors, with the help of other hormones, control the division of the hematopoietic stem cells. Actually, when the number of red blood cells is large, some growth factors, with the help of other hormones, suppress the division of the hematopoietic stem cells. And in the converse case, they will promote. H, as I said at the beginning, denotes the harvesting of red blood cells, such as tapping therapy, sampling blood, or blood donation. And tau is the harvest lag. Let's turn now to the second section. So let's begin this section by defining the following closed, convex, and bounded subset omega of the Banach space of all T-periodic continuous functions equipped with the usual supernorm norm. For simplifying our results, let's adapt these notations. Moreover, we assume these assumptions to be true. H satisfies inequality number 2, and these three inequalities hold. Here from lemma 1, we can point out that finding an antiperiodic solution of equation 1 is equivalent to finding an antiperiodic solution of integral equation 6, where the kernel here is Green's function and is given by this expression. It's worth mentioning that the obtained kernel satisfies properties number 7 and 8. Let's now move on to the main results, and let me start by talking about the existence outcomes. So the main objective behind this section is to find some sufficient conditions that ensure the existence of at least one solution of equation 1. And for achieving this, we will use a powerful technique based on the schauder'sfixed theorem combined with the Green's functions method. For this aim, and by virtue of lemma 1, we find an integral A given by expression 9. It follows that x is solution of equation 1 if and only if x is solution of the integral operator A. For applying the schauder'sfixed theorem, it suffices to show that A is well defined, continuous, and compact, and this inclusion is true. By virtue of the periodic properties, lemma 2 clearly shows that A is well defined, while lemma 3 proves that it is continuous and compact operator. The proof of this lemma is basically based on Ascoli-Arzelà theorem. So obviously, the departure set omega is uniformly bounded and equicontinuous. Hence, as a consequence of Ascoli-Arzellat theorem, omega is relatively compact, and since it's closed, then omega is compact set. So, to show that A is compact operator, it suffices to show that it is continuous. Indeed, for x and y in omega, condition 2 and Green's function property 8 led to this estimate, which shows that A is Lipschitz operator and hence it's continuous, therefore A is compact. The lemmas 4 and 5 under conditions 3 to 5 ensure the correctness of the last condition of the schauder'sfixed theorem, which means the operator A maps the Claus inverse and only subset omega into itself. Now, and based on the previous lemmas, we state our first theorem, which establishes the existence of at least one solution. So it follows from the lemmas 4 to 5 that all conditions of the schauder'sfixed theorem are satisfied. So there exists at least one fixed point solution of the integral operator A, which is the positive periodic solution of equation 1. Moving on to the second part of this section, which discusses existence, uniqueness, and stability results. So for the existence and uniqueness results, in addition to the aforementioned conditions in theorem 1, suppose condition 10 is fulfilled. Then equation 1 has a unique positive periodic solution that belongs to omega. Indeed, from lemma 3, for all x and y in omega, we get this inequality, and from condition 10, A is a contraction, and as a result of Banach contraction principle, A has a unique fixed point solution in omega, which is the unique solution of equation 1. Here we present our last theorem, which establishes the continuous dependence on parameters of the unique solution. And for this, let x be the unique solution of equation 1, so x satisfies the integral equation x6 as follows. And let's assume there is another solution of the perturbed equation with small perturbations in harvesting term and production rate b also satisfies the integral equation 6. So in view of conditions 2, 10, and Green's function property 8, we arrive at this inequality, which shows that small variations in production rate b and harvesting term h led to small variations in the obtained solution. So the unique solution obtained of equation 1 depends continuously on parameters b and h. To validate our obtained results, I will present two illustrative examples. So, in the first one, let's consider the following iterative differential equation given by expression 11 in the subset omega 1. Here, this term is the loss rate of red blood cells. This one is related to the production of red blood cells per unit time, and this is the harvesting function. We choose a period of 19 days, since the period can vary from few weeks up to few months. So in this case, and for these values, we can easily see that the aforementioned conditions of the existence theorem are satisfied. Also, the additional condition 10 in theorem 2 is satisfied. In addition, if x is the unique solution of equation 11, and if we assume there is another solution of the perturbed equation with the perturbed parameters, we arrive at this inequality. So in this example, and since all the aforementioned conditions in theorems 2 and 3 are satisfied, equation 11 has a unique positive periodic solution in omega 1 that depends continuously on harvesting term h and production rate b. In the next example highlights the power of the existence theorem to establish an existence result even when the Banach fixed point theorem cannot be applied. And for this, let's consider the same iterative differential equation of the previous example with the same period, but in this new subset omega 2. Here, in this case, we can easily verify that the aforementioned conditions of the existence theorem are satisfied. However, the additional condition in theorem 2 is not satisfied, which means that in this case, in equation 11, has at least one positive periodic solution that belongs to omega 2, which is not necessarily unique. In conclusion, let me briefly recap our main steps followed in establishing our main findings. So, as I said at the beginning, our key task in this work is to prove the existence, uniqueness, and continuous dependence on parameters of the positive periodic solution for our model by using an efficient technique that combines between schauder'sfixed theorem and Green's functions method, where the main idea here consists to convert our problem into an equivalent integral equation where the kernel is Green's function. Next, with the help of some properties of the obtained kernel as per the theorem and under some assumptions, we succeeded in constructing an integral operator A, well-defined, continuous, compact, and maps the departure set omega into itself. Finally, we have concluded that all requirements of the schauder'sfixed theorem are satisfied. So, if x is fixed point solution of the integral operator A, then x is solution of the integral equation and also of our problem. On the other side, besides the assumptions of the existence theorem and under an additional condition, the contraction Marwa principle ensures the existence of a unique fixed point solution of the integral operator A, which means our problem has one and only one positive periodic solution that depends continuously on parameters. Here are some of our main references. Thank you very much for your attention.